we see that we have this equality, and the radical space of A is an ideal, okay? This position that say this quotient space is a semi-simple Banach algebra. Please note that an algebra is semi-simple whenever the radical space of this equal to 0, so that for this proposition we must prove that the radical space of this quotient space equal to 0 only, okay? So let me write this for you. Okay. Proposition let A be a unital Banach algebra then the rod A is closed ideal and this is a semi-simple Banach space. Is a semi-simple Banach algebra. Okay. For the proof, we can prove this by some steps. At the first we see that this is an ideal and we see this in the previous session, okay? We see this in the previous session. The radical space of A is an ideal, so we prove this. Is an ideal in A. And also we can prove by this method if, for example, x belong to A and y belong to the radical space of A, then with this equality we see that EA minus BA is invertible for any B in A, okay? This shows that for any B in A, EA minus sorry, this is Y, not A. No, EA minus B XY must be invertible, okay? Because this is an element of A. This is an element of A. We know that for any B in A we have this, okay? And this is an element of A. So that EA minus BY, this is a B prime, for example, must be invertible. And this shows again that XY must be in the radical space of A by this again, because for any B in A, EA minus XY is invertible, okay? And this is another proof for this fact that this is an ideal for an x and in A and y in the radical of A. XY is in the radical of also it shows that this is left ideal, and also we can prove that this is a right ideal. Okay, so this is the second proof for this fact. And also we must prove that this is an ideal, this is a closed subset. Let me write. Is closed in A. Because if we consider an element such as X in the closure of this set, there exists an sequence in this space such that X equal to the limit of Xn. Okay, there exists a sequence such that X equal to the limit of Xn. This shows that for any n in n, Xn must be equal to the radical space of A, and we know that this is equal to intersection of all maximal left ideal. Maximal left ideal. Okay, so that for any n in n, Xn must be belong to M for any maximal left ideal. This shows that X equal to the limit of this sequence must be belong to the closure of M, but we know that maximal ideals are closed, so that this X must be belong to M, and so that X must be belong to the intersection of these M's, and this is equal to the radical space of A. Please note that we assume that it belongs to the closure of this set, and we prove that this X must be belong to this set, so that this closure is a subset of the radical space of A, and it shows that these two are the same, and it shows that this is closed. We use from two facts. Please note that the first fact is this, that if this is a metric space, for example, okay, and A be a subset of X, X is an element in the closure of A if and only if there exists a sequence in A such that X equal to the limit of Xn, okay, and we use from this if X belongs to the closure of this, there exists a sequence in this space such that is the limit of Xn. And another fact is this, that A is closed if and only if the closure of A equal to A, okay? By these two facts, we see the proof of that the space is closed. Now we must prove this fact This is a semi-simple, okay? For this, denote by row from A to this space the canonical projection the canonical and you know this projection for any A in A, row of A equal to A plus the radical space of A, okay? This left coset of the radical space of A, okay? If X belong to A and X not in the radical space of A, then there exists a maximal left ideal G with this property X not belong to G. And this is very trivial because we know that the radical space of A equal to the intersection of all M such that M is a maximal left ideal in A. Okay, and this is our next step. Okay, so if X not belong to this radical, X not belong to this intersection, so X must be outside of this maximal left ideals at least in one. Okay, there exists one, because if X belong to all of this, must belong to this intersection. Okay, so there exists a maximal left ideal such that not contain X. Now we see that row of G, this G, or G plus the radical space of A, is a maximal left ideal in this space. You know that this is set of all elements by this form. Okay, the set of all left cosets in the radical space of A. This is maximal because if J plus the radical space of A be a subset of P, and P is a left ideal in this space then if we put t, for example, equal to the set of all x plus r such that r belong to the radical space of A and x plus the radical of A belong to P, because we know that elements in P have this form. So we consider this set. This is a left ideal in A. Left ideal in A. It's very trivial, but it is the left ideal, because if we multiple any element in T, this is an element in T again, okay? For any x in the radical space of A and R in the let me write by this manner. If x the radical A belong to P and R belong to the radical space of A and A belong to A, we see that A plus x plus R equal to AX plus AR. Because this is an element of this P, so that if let me specify this parenthesis by another color such as this, we see that this is an ideal and this is contain G, but G is an maximal ideal so that J must be equal to T, and so J plus the radical space of A must be equal to P. If we consider this not equal to a whole of this space, okay, this quotient space, and P is left ideal, we see that this must be equal to P. So that this is the maximal left ideal, and also rho of x, because we define this function rho of x, or x plus the radical space of A in this space, the image of G. Thus x plus the radical space of A is not in the radical space of this quotient space. Because we have is not in P of G, sorry. X not in G. Let X, we consider a maximal left ideal such that X not belong to G, so that X plus the radical space is not in P of G, because P of G is G plus the radical space of A. Okay, let me write more company. Is not in G plus the radical space of A, and this is the maximal left ideal. A maximal left ideal, okay, so that This is not in the radical because the radical space is the intersection of all maximal left ideal. Okay? So that if not belong in the radical space of A, then X is not in the radical space of this quotient space, or equivalently if X plus the radical space of A is not zero element of this space, okay? Zero element of this, because we know that this is zero if and only if this is equal to the radical space of A, or X belong to this left ideal. Then X not belong to the radical space of this space, okay? Radical space of A. And this shows that this radical space is zero only. If X non-zero, not belong. So the radical space of this space equal to zero only. Zero of this space, okay? So this is a semi-simple space. Is semi simple, okay? And the proof of this is complete. This is a semi simple Banach, okay? And we have this proposition: let A be a unit of Banach algebra, then the radical space of A is a subset of the set of all quasi-nilpotent elements in A. We recall that A is quasi-nilpotent if and only if the spectral radius of A equal to 0. And proof of this is easy, because if we consider A in this space, let A belong to the radical space of A, then this is an invertible element. By these facts, okay, by these facts, A belong to the radical space of A if and only if EA minus BA be invertible. Okay, this is very applicable. That A is an element of the radical space of A if and only if for any B in A, EA minus BA be invertible. Okay, by this fact, if we consider A to the radical of A, EA minus, this must be invertible because EA minus this space or this set let me like okay, EA minus A divided by Z equal to EA minus this multiplied by A, and this is equal to EA minus this real numbers EA multiplied by A, and this is an element in A. Okay, so that this must be invertible because for any B in A this combination must be invertible. Okay, this must be invertible. So if A belong to the set of all the set of radical space for any non-zero element EA minus A is invertible, and this shows that for any non-zero element this is in the sigma of A. Okay, please recall that. Row A of A is the set of all complex numbers such that EA minus A divided by Z is invertible and sigma A is the complement of this. So that this is not belong A. Okay, this is not belong in sigma A. And so this is zero element only, and so this supremum must be equal to 0. Okay, for any non-zero element this is not in sigma A. This shows that any non-zero element is not in sigma A, or sigma A equal to 0 only, and this shows that A is a quasi element in A. And for 2, suppose that A is a left ideal of A with this inclusion. I is a subset of quasi nilpotent element in A, then I must be a subset of the radical space of A. And the proof of this is easy again. Let A belong to I, to this set. For each B, BA must belong to I because I is a left ideal. So BA must be belong to DA because I is a subset of DA. Now by 1, EA minus BA is invertible, and hence A must be belong to the radical space of A, because for any B in A this is invertible. Okay, this is invertible. Please note that if BA belong to this shows that this is invertible, because only for 0 EA minus BA divided by Z is not invertible. Okay, and 3 is easy again. In the case where A is commutative, this radical equal to the quasi-nilpotent element of A. And this proof is easy again. Take A in this space and B belong to A. We have this. Please note that because we consider A is a commutative algebra, this is important that if For example, BA multiplied by A inverse B inverse equal to identity, okay? Because these two is identity and then. So the inverse of BA equal to the inverse of A, the inverse of B. And similarly, the inverse of this equal to this space. Because this is BA multiplied by BA, okay? If we multiply this by the inverse of B, the inverse of A, the inverse of B, the inverse of A, the inverse of B, n times, this is equal to E of A. This is n times, and this is n times, okay? These two are identity and up to the n. So that this is the inverse of this. Or is multiplied by this equal to the identity, shows that this is the inverse of BA, and inverse equal to this, okay? But if A considered commutative, we can replace the situation of these two elements, okay? And we have this. For equal to AB, 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 we can replace the place of these two. This equal to AN, PN, okay? Because A is commutative. And so that this is equal to this, and this is less than this, and this tends to 0. Hence, the spectral radius of BA equal to 0, because the limit of this equal to this, okay? And BA belong to the quasi-nilpotent element of A. Thus, this is an ideal. Consider A to this and B to A. BA belong to this, and so this is an ideal. And so the quasi-nilpotent element of A equal to the whole of radical space of A, okay, by 1 and 2, because by 1 we know that this is the subset of this, and by 2 This is a subset of the radical space of A, so that these two must be equal. Okay. We continue in the next session. Dear students, do goodbye. Thank you.